talk about just sort of the basic mathematical formulation when we get to unsupervised algorithms. And the classic case you look at there is you talk about Hebbian rule. So you're talking about something that's going to be a Hebbian learning. And then the question is going to be, all right, so what would I see? Well, Hebbian learning, remember, we're going to be talking about taking the outputs and the inputs and cross-correlating them. It sort of goes to this approach of saying, if I have a neuron input and a neuron output that are both firing, I'm going to increase the weights accordingly. Very loose, very loosely kind of defined there, but at least it gives you a starting point of how that might come into play. And so this is how we typically think about a sort of Hebbian rule. You think about having an input vector and an output vector, and then you have a weight matrix in between. This is a vector matrix multiplication, and we can continue there. We could have some nonlinear dynamics after y. If it's afterwards, it really doesn't affect what we're doing here, unless I really try to incorporate it. And there's many ways to continue on, but the core physics kind of shows up here, one way or the other. And so what I'm going to get here is a tau, which is going to set the time constant times the change of the weight with time, is going to be yx transpose, so an outer product. So this kind of accounts for all of the w, which is then going to be really w times xx transpose. Looking at this over slow time scales, which would be what you'd expect for the weights, I'm going to be getting an expected value of xx transpose. That's going to give me a correlation matrix Q. Remember that the x variable, the inputs, have to be going much faster than the actual inputs or the actual weights. They have to be separated time scales, and that sort of creates a whole formulation, both in terms of the fact that I've got my inputs are zero mean. I'm going to be popping out a correlation matrix because of the product, and my weights basically just come straight through, which means I basically end up with this nice matrix differential equation. Tau dw dt equals w times q, and you're like, great. And so let's just see where this goes, right? Well, Q, of course, is going to be a covariance matrix. I can look at this in terms of its eigenvalue and eigenvectors, where lambda is going to be a diagonal matrix of the ordered eigenvalues, and E will then be a matrix of all of the eigenvectors ordered by the lambda. Now, understand this, that lambda is now always going to give me positive or zero eigenvalues. So what do I see out of this? Good question. Let's actually go right to sort of the projecting this into the eigenvalue space. So W is equal to AE transpose. And as you solve through this, you have the AE transpose here, the E transpose E cancel out. And then I get a double E transpose pre-multiplied by E. They all go away, and I get this nice sort of formulation of A is equal to A times lambda. Lambda is a diagonal matrix of all the eigenvalues. This means for each of the vectors of A, I could consider each of them, there's a whole set of vectors in that matrix. Each of those now has a corresponding lambda sub k of each of the ordered lambda sub k's in there. And then I could say that those matrix A sub k is going to be A sub k 0, and I could proceed from there. And you're thinking, great, and then lambda is always positive. Ooh, now I got a problem, don't I? Because this is going to be unstable everywhere I go. Now what do? So you go, well, this is unstable. I should never worry about this again, right? Well, let's think about this for a second. You might say, so again, the next question is why even bother? But you said, what if I can normalize W? Maybe I normalize that input by a norm of A1, A1 being the largest of the eigenvalues. Imagine a norm, pick kind of a structure for this. Obviously, this will depend on the initial conditions, which will have some norm in it. But notice what this is then going to give me. I'm going to get e to the lambda m minus lambda 1, the largest of the eigenvalue. This is not true for when m is 1. Or for when k is 1, this should be lambda sub k here. And so this is always going to converge to 0. So this is now stable. And what's interesting is that for when k is 1, it pretty much just stays there. So now I begin to notice that I might be able to converge to the dominant eigenvalue. Now that gets interesting. If I can do the normalization, there's something there. And if I can do it for 1, I could do it for several by just proceeding in a similar process. How I would do that still to be figured out algorithmically, but you can kind of see that there's something rich in this, and one of the things you're looking for here is often what you talk about as principal component analysis. Often talk about as PCA. And what you're really saying is, given that I have, a lambda, which is ordered eigenvalue of E, and I have of Q of a symmetric matrix, well, something interesting happens, right? And I can end up solving for lambdas. I can solve for E's from X, which X being XX transpose giving me the correlation matrix. This is really useful. E will then be a unitary matrix. Unitary meaning it doesn't affect the signal power. Well, that's really useful, right? So that means that lambda still has all of the definition of the signal power of Q. But something else comes up. Notice if I look at YY transpose, right? Now that would be the correlation matrix of the output, if that were true. Well, that's YQY transpose. I get some E's, those all cancel out, and it's simply just lambda, which means I've got the signal powers in an ordered form. I've got everything uncorrelated, and I've got sort of this going through a unitary matrix. That uncorrelated side is really, really interesting, because now it says, well, wait, uncorrelated, because now it's uncorrelated. So now everything else out, that we often talk about this as a whitening filter. But further, really interesting about this is that I can, since they're ordered, I could go, well, wait, how many of them are significant? Because if a couple of them are there, but they're tiny, why not just get rid of them? Because they're probably causing more trouble than they're worth. So just only take the inputs that I need. Or it might tell me for this particular set of inputs, these are the things that are statistically significant and the rest are basically negligible. This becomes huge as I start saying, well, what could this go into a typical network? What kind of pre-processing helps me clean up a particular network I'm building? And there's a lot of different aspects I could look at this, but this kind of a structure that could be calculated in sort of a normal differential equations, maybe taking these and modifying them in some way, turned out to be a very, very powerful technique.